Hello, good morning, good afternoon, good evening, wherever you are around the world. We really appreciate your time for joining us for today's webinar, Validating Air Conditioning Design using a Cloud-Based CFD to Improve IC Layout Design. First of all, before starting this webinar, I would like to ask you if you can hear me clearly and loudly. I mean, there is, for people who are new with this tool, GoToWebinar, there is this bar just from the side of your screen where you can, where you can raise your hand. So please, if you can hear me clearly and loudly, raise your hand so I can make sure that everybody can hear me. Okay, perfect. I can see already a lot of hands raised. Okay, perfect. Thank you so much for everybody. So you can drop your hands now. Okay, thank you so much. So as I mentioned before, so this webinar we will discover why we should use simulation for this application of air conditioning. This air conditioning can be different application for an IT room or for for a place where there is humans, and so there is a lot of applications. So first of all, as you have already maybe mentioned, not said, so I'm not David Heine, who's supposed to present today, but for some scheduling issues, so I will take it over. So my name is Akram Mufak. I'm a technical account manager at SimScale. I hold a bachelor degree in aeronautical engineering and several years experience in CAE, with experience including CFD, CAD, parametric optimization, and aerodynamics, and I'm glad to present for you today. So as I mentioned before, so we're going to talk mainly about the effect of simulation and the effect of simulation in designing better air conditioning systems. So as an expert in this field, one of the things that I'm facing every day in my daily work is that people, they ask me, what is the value of using simulation, and especially CFD, let's say, in designing my products? Because there is already methods to design a product, but why exactly CFD? So here in this slides, we're going to cover why CFD is important and why CFD can bring more benefit to your company and your organization. So to illustrate this point, here in front of me I have this curve that is showing in the x-axis the design process timeline, but this design process timeline can be for a car or a building or any product that we want to design. And the y-axis, we have the product cost and performance. Usually we try to make the performance as maximum as possible with reducing the cost. But the truth is we can't increase the performance with low cost. So we have to pay the price to get this performance. And usually, I mean, this plot will show us exactly how the price and the cost of this product to get this performance will develop over the timeline of designing this product. So this curve, as you can see here, this is the first stage of the product design. So we are in the design phase. We are not in the production phase. So in the design phase, we can see that the cost of the product rise really, I mean, the gradient is really high over here, and this is because of this first step in the design process require a lot of inputs from the engineers, and it's at this point is the first part of the design process timeline where we can see that the cost rise significantly. But at certain point, we can see that this increase will drop a little bit, and we can see it's almost constant here. And exactly at this phase in the first step of the design process timeline, where simulation is required to reduce this cost to achieve better performance. And this is exactly the main motivation of this webinar, is to show you how you can use simulation to reduce the cost that you will spend to get the maximum performance in the first stage. And of course, if we talk about another side of the product development, it's the realization where we produce the thing, so we can see that the cost is completely the cost plot compared to the design process timeline is completely different. And so the matters that we are always trying to solve when we design a new product, it's to make sure that this design we are taking the right decision earlier in the design process. And what we mean by this, it's this first stage of the timeline. This decision making or decision of the design, which is the better design, it can depend on the project. So it can be the low cost or the low energy consumption, or also keeping the deadlines always under the deadline, or the lower failure risk, or it depends on the product, but can be like reducing the drag of the product, or I mean this functions depends on the product, but also depending on the role of the person who is designing, or who is involved in the design process. So for example, if we are talking about the designer, usually the designer, he's mainly interested about maybe lower failure risk. But if we talk, for example, about an engineer, he's mainly interested about lowering the energy consumption. But for example, if we look at this from another view, for the manager, his main interest, maybe it can be the cost, so lowering the cost. So in this presentation today, we're going to see how simulation will affect all these rules. So how the designer can get better design faster, and how the designer or the engineer can understand the physics better, and how the manager can cut the price and the cost of the whole design process. So we will see how all these rules will benefit from the simulation. So to do this, I mean, there is different approaches, and simulation have been in in the field from years now, and over 30 years or more in the industry. But usually simulation have a lot of barriers. So first of all, talking about accessibility, simulation have been always only for people with large companies, that they have the budget, they have the infrastructure to run this these simulations. But the concept that we bring with SimScale is to cut all these barriers that engineers, managers, or designers are facing in using simulation. And one of the most important things is accessibility. So with SimScale, you can simulate without any problem using a free community plan, where you can just create an account and you can log in and you can run your simulation. And of course, by making the projects publicly open, so you can operate and you can design and you can iterate without any limitations. Another really important thing is the cost, because usually with with the different concept of the softwares, where you have to pay thousands and thousands of euros to run your simulation. But it's not only the CFD tool, because in CFD the most important thing also, it's the operation system that you are using to simulate. So you have to invest money in the computer that you want to use, I mean the hardware, and also the software. So the cost, it's really a major barrier in the field of simulation. And with SimScale, we are offering different subscription models. So you can subscribe yearly, or we have different subscriptions that will fit to your needs to help you design better designs and products. And most importantly, it's for everyone. Like I said before, simulation have been always only for the high-end people in the engineering, and most of the startups cannot access to the simulation. But now with our concept of the public projects, and people can share their ideas, so now it's for everyone can create an account on SimScale and run a simulation. And also about the application, because simulation, in fact, it's not only CFD, but there is different applications. Let's talk about structural simulation or CFD that we refer to, computational fluid dynamics or thermal dynamics, or also more physics like particle simulation and so on. All these different disciplines can be modeled with SimScale in one user interface on the cloud. And maybe what I can do, so I can give you a quick tour over here on SimScale and how you can create an account. So all what you have to do, you go to simscale.com, then you have the possibility over here to sign up. So you just click on sign up. The process is really simple: name, an email, and number. So just some registration process. Then as soon as you do this, I mean, you will be able to log in, and I mean, you can log in and you can start simulating directly. As you can see, just a simple process. You can create an account and you can start your design process and understanding and predicting the behavior of your product and system even before building any physical prototype. So let's jump back to the presentation. Of course, I mean, as an engineer, and usually when I talk, of course, about, I mean, I talked about this before, our public projects. We do have a lot of public projects that you can use as a template to discover new physics that you are not maybe expert with. Okay, but usually, I mean, for an engineer or for a manager to talk about a new topic, it's okay, but can you improve this? Can you prove that simulation can really bring something new to the engineers, to the designers, to the managers? And nothing can help us to demonstrate this than a real case. And this is exactly what we're going to discover now. So we have a scenario of a cooling air supply in an IT room where we're going to see how simulation can really bring benefit to your company and your organization by using simulation and virtual modeling. So in this case, as you can see, we have a room, an IT room. So what we can see, we have a cooling air supplier or the inlet where we have, from where we were going to have the cold air. We're going to have the outlets with over the chimney over here, and also we have heat sources. So these heat sources here we are modeling like an IT room, but these heat sources can be human being, can be anything that have heat, so we can model it. And our main goal in this simulation is to make sure that we have a cooling, an efficient cooling all over our room with the same cooling distribution, or with the same, let's say, homogeneous cooling all over our room. And this is exactly our our target from this study. So as we can see here, this is an initial design. And what do we mean by initial design? So first, when you design a product, so let's consider this as a product. So when you design this product, usually you start with an idea. And our first idea was to put the inlet of the cooling system from here. But it's like one from million percent, that one from million possibility that this will be the optimum design. And if, for example, we rely on the old school technique of creating a real prototype of this and test it, this will be really time consuming and will be really expensive to do this, because to build the test and also to test it, this will take a lot of days to create the model, and also to get accurate representation of the values. This will take a lot. So after you create the model, so we have an idea, but now how I'm going to design, or how I'm going to run this simulation. So first of all, you need the CAD model. So we have to import a CAD model into your software, and in this case we are using SimScale platform. So we import the CAD model directly from your CAD software, and as you can see here we have our graphical user interface. Then the second step will be to generate, of course, generating the mesh, doing the spatial discretization using a discretization of the mesh. Then we apply the boundary condition and so on. Then the second step will be the simulation. So when we apply boundary condition, we run the simulation. Everything is done using web browser, so we don't have to install any software locally, and there is no maintenance or these barriers that we face usually with the traditional approach of using CAE tool, because everything is done on cloud. And later you will see the design, you see the post-processing, and also based on this post-processing you can make your decisions, you can iterate in your design to find the better design. So this is the workflow of using simulation and exactly using SimScale, because this this process or this workflow can change from software to another, but using SimScale you're going to get all the process using one graphical interface, which is really beneficial to cut all the problems of moving from software to another. Okay, so now let's talk more about simulation. So we did the simulation of this IT room that we have showed before, and now we are visualizing the results. And here where the engineer and the designer can really see the benefit of using simulation, because to see this color, so here we can see these colors of the pressure, the temperature distribution over our heat sources. But in reality, to see these colors and to understand what is going on when I start my cooling system, it's really difficult. But this will give you a real physical view of about what is happening here. And maybe we can do a quick interpretation of this result. So we can see here we have this inlet. So the inlet is from here, and we can see that the air is coming. So the blue color, or the green color, it's low temperature. The red color, it's high temperature. And we can see that we don't have a homogeneous distribution of the temperature over our heat sources. And our most important criterion, or our objective here from doing this simulation, is to see if we have homogeneous distribution all over our heat sources. And now the designer and also the engineer, they sit together and they start thinking about finding the best option, or finding the optimum design that will help you to get the smooth, or let's say homogeneous distribution all over this heat sources, or in this case our clusters or computers. So to do this, we use different post-processing techniques, from using slices. As you can see here, we can use slices to see, and when we use the slices, we can see the effect what's happened. So we have the flow is coming here, then this cold flow, the blue one, will hit the first computer, and what will happen, we will have a recirculation region here. And that's why the computers behind the first one are really hot, and this is the main reason, because we are stopping the flow in front. But actually, if we didn't run this simulation, we were not able to understand what is going on. Maybe we know that the last computer over here is overheated, but we don't know, so we can't predict what is happening, and we can't see the temperature like this if we don't run a simulation. So this is really beneficial, the beneficial aspect of using simulation. So as we talked before, so this is the initial idea, and we run the first simulation, we have seen the first results, but now this is the most important thing, is changing the design and making better designs. And based on what we have seen that the flow have been stopped by this first computer over here, and that's why the flow, the cold air cannot go to the other heat sources, and that's why we have this problem of non-homogeneous distribution all over our heat sources. And the next step I mean, of course, this is this case, but for example, if you are doing another application, of course, the decision can be changed, depends on the objections that we are looking for. So based on the analysis of the results that we got from this simulation, we have decided to come with a new idea. So we have found that the problem was happening because this flow will hit the first row of computers, then the flow will stack over there with this vortex that will be created here. So our decision or our idea was to create a new inlets of the cooling system, but this time we'll put it here, like we call it lifted floor IC, and this will help us to make sure that we're going to have the same distribution of the air all over our room. And one thing that we have to not notice here, that we are using the same flow rate and the same flow rate between the two scenarios or the two designs. So the same quantity of energy that you will waste to create this flow over here, it will be the same over here. But now let's see the effect of just changing the inlet and creating multi-inlets close to the heat source, how this will affect our simulation. So here what we can see this iso surface that is representing thermal or the temperature, and we can see for the initial design that the flow is coming from this inlet, and then like we discussed it before, that it will be stopped by these three the first row of computers, and this will create problems later for the last row because there is not enough quantity of the air that will reach to the last one. But from the other side, what we can see from the new design or the new idea that we have based on our analysis of the result, we can see that we have almost homogeneous distribution of the temperature all over our clusters, because we are giving the same quantity of air to each computer, and this will help a lot to cool and to make sure that we have a homogeneous distribution of temperature all over our room. And of course, like I said before, this is a case of IT room. It can be different application for human beings, or maybe in stadium or theater. Of course, there is a lot of public projects available that you can check on our public library, and this will help you to understand better different applications, not just one application of IT room. As you can see here, so it's more uniform compared to the other one, where we have more concentration of the cold air here, but here it's like homogeneous for the same period of time. Okay, so also here we can see using a slice, and also we can use this LIC to visualize the vortices and recirculation regions. So the top side, the top view or the top figure represent the initial design, and we are creating midsection in our room, and we can see that we have this cold air that is coming from this inlet, but it's clear that just after the first row of computers, this air start to get hot, and the last row is like almost in hot region. But if with the new design, we can see that we have almost homogeneous, almost the same distribution of temperature all over the three different rows, and this will help us to get better, efficient cooling all over our room. Okay, but it's more interesting to talk about numbers than just colors, and this is what we can see here. So as I mentioned before, we are using the same inlet flow rate. What I mean by this, we are using the same energy to generate this cold air for the two different designs. So we are not increasing the flow rate, for example, for the new design, but we are using the same flow rate and also the same energy to generate this flow rate. And we can see clearly that using simulation and just by changing the design a little bit, we have decreased the temperature by, 12.5%. It's just from one iteration. Imagine if you dig deeper into this problem and try to understand exactly what caused this problem and change the design based on what you're looking for. I'm pretty sure that you can get more improvement after the fifth or the sixth iteration, and here we are showing the average temperature over the heat sources. So it's really beneficial. Engineering talking, design, because you can explore more efficient designs, and also talking about the decision maker or the person who is the manager, because this will save a lot of time and also a lot of money, because this will reduce the energy that you have to to generate such a cooling. So this will reduce the energy. In consequence, this will reduce also the money or the cost of this project. And of course, there's a lot of people, they think that simulation, it's just colorful pictures. Of course, it's really nice colorful pictures, and I'm not ashamed of saying this, because I really enjoy looking at these pictures and see exactly what is going on, understanding the problems, and also this will give me a better view about what is happening. But the truth is, CFD nowadays is getting like really and really close to the accurate answers. Of course, years ago, 20 years ago, maybe simulation was not really accurate, but now simulation is really accurate and is giving results that you can compare to the experimental values and results. And this is exactly what I'm going to show you here. So the accuracy, it's a key factor in using simulation, and we are really we have really robust and trustable solvers that we are using SimScale. And here we can see an example. So in this example, we do have this room with four heat sources. These heat sources can be humans, can be the same example like we have showed before, but it can be anything. And what we can see here, we are showing these three points where we are taking real physical tests. So we did physical tests, and we are using real experimental results to compare our numerical simulation results to really make sure that what we are showing, it's accurate. It's not just colorful pictures that you will like it and you will say yes, but it's not trustable. But here you can really see this here. So what we have two we are taking just 2 points, but of course we do have a validation case that you can find it on our documentation. It's full validation case where you can go through the paper and understanding exactly the accuracy of our tool. So what you can see here with the blue line, this is what SimScale is given after doing the simulation. And the red line, it's the experimental test. And of course, there is a value of velocity, and from the y, it's the height. And what we can see is that the result that we are getting is almost perfect. Given to the, of course, we are using a couple of points here to plot this line, but here it's like just 5 points. But we are getting really accurate results that we can compare to experimental results. So what we can say here, that simulation, if you can tune it correctly, and this is what we did at SimScale, and if you know how to use it, you can reach really trustable results that you can use directly in your production. Okay, so let's wrapping it up now. So first of all, we have talked about using simulation in the design process and in designing a product, and how simulation can save time, can save money, can really save your budget, and also can help you to iterate and to find better and accurate designs. And this is exactly what we're going to see here. So first of all, this work, the simulation that you have seen here, so talking about the engineering time, the manual time, the time that the engineer will spend with the software to solve this problem, it's 2 hours. It's just 2 hours to set up this case because we are using really simple, straightforward process or workflow to set up such a simulation. The computation time, taking consideration that this is transient simulation, but as I mentioned before, we are using cloud machines that you will use to run your simulation instead of a limited computer that you have, maybe a laptop. Or so this simulation, transient simulation, takes just 7 hours. 7 hours, so it's really fast for an transient simulation, and we have used over 500 core hours, which is the unit that we are using because we are running a parallel run with up to 32 cores, and for a given time 7 hours, so it can be 400 core hours. So return, after doing this simulation, what is the benefit now? So the benefit, we have reduced, just by doing one iteration, we are not talking about doing real optimization study, but just after one iteration, we were able to reduce the average IT facility surface temperature, or the average temperature, by 12.5. So imagine this 12.5, when I'm talking like this, you will take it as a number, but this 12.5 will reduce a tremendous amount of energy that you will put over a year to cool this room the same efficiency. So this will represent a cost that you will add to your product by the end. So not only say it's really fast, but also will help you to improve the performance of the design, and also will reduce the cost of the design, and most importantly, you will have a design confidence, so you know that your design is something trustable that you can rely on. Okay, thank you so much, everybody, for your time. I really appreciate it. It was really pleasure doing this presentation for you today. So I tried to keep it really tight, 30 minutes. So as you can see here, I have my email address. It's available here. Whenever you have questions, or you need support, or you need to explore SimScale more, you can reach out to me, and I will be glad to answer your questions. I will promise to answer your questions. Thank you so much. Have a nice evening. Bye-bye.